Good morning, I am Celia Tanarro. I work for the European Chemicals Agency for the guidance team, and I have coordinated the development of guidance on nanomaterials that was published in May 2017. That's the topic of the webinar today. So there you can see the agenda in Helsinki time. And you can see that we will have several presentations. My presentation is an introduction giving an overview of the ECHA guidance on nanomaterials and also some general issues about the webinar. That will be followed by more in-depth presentations from my colleagues on each of the guidance that was published last May. So first, some general issues about this webinar. So you have a questions and answer panel that is in the bottom right-hand corner of your screen. You have a tab, Q&A, and pressing there you can send us questions about the presentations that we are making, and also you can send us messages if you have any technical difficulty. In the question and answer panel, you can submit your question at any time, and we will answer as many questions as we can, but maybe we will not be able to answer all the questions, and if that's the case, you can send the questions that we have not answered to your National Help Desk or to our ECHA Help Desk. Also, the recordings of this webinar will be published in our YouTube channel, and you will be able to find the guidance, the webinar material, such as the presentations, in our website. So now to the topic of the webinar today, that is the REACH guidance on nanomaterials. The first questions could be why we do need a specific guidance on nanomaterials. So even if nanomaterials are not mentioned explicitly in REACH, they are covered by it because they are considered to be covered by the substance definition of REACH. Also, the Commission did a regulatory review on nanomaterials in 2012, and there it was clarified that nanomaterials are covered by REACH and that they can be either substances on their own or nanoform of a substance that are included in the same registration dossier of a bulk substance. So you will have both the bulk and the nanoform. That regulatory review also recommended to develop new REACH annexes that clarify the requirements for nanomaterials in a more explicit way, but those annexes revised are not available yet, and for that reason, when we did the revision of our guidance, we did it in the current regulatory framework. But even if there was not any change on the regulation, we could develop guidance because we had issues that we could clarify and that could help registrants when they need to register nanomaterials. For instance, we had some experience gained during the dossier and substance evaluation, and for that reason, we can give some advice to registrants. Also, we have better reporting possibilities. So for instance, you can report better nanomaterials in Euclid, and you also have a new feature that is the assessment entity that will help you in the case of complex substances. For instance, substances that have several forms, and that is in many cases the case for nanomaterials. Also, we have included regulatory and scientific developments. For instance, there are new testing guidelines at OECD, new standards, etc. And all that has been included in the guidance when relevant. And also, we had some feedback from registrants, and we have discussed how to register nanomaterials with them. And from that discussion, we already had some lines that we felt that we could put into guidance to provide advice for the 2018 registration deadline. So now, which guidance do we have for nanomaterials? So first, we decided that there were some issues where we didn't have any guidance at all for nanomaterials, and that it was important that we gave advice for those topics to registrants. For that reason, we created two new documents. So a best practice document, how to prepare registration dossiers that cover nanoforms, and an appendix to the guidance on grouping and read across for nanoforms that will give you specific advice for nanomaterials. The reason of doing this is because when you are registering a substance that includes nanoforms, you are going to have to cover situations where you may have a variation in size, in shape, surface treatment, etc. And we believe that it was useful to give some advice to registrants on how to distinguish between the different forms that this variability may bring. And also because for all those nanoforms that you have identified, it is clear that you need to cover all the hazards. And for that reason, we also have that guidance on grouping and read across that will help you to determine whether the hazard data that you have are applicable, for instance, for another nanoform of the substance. You may have data for the bulk form of the substance, and you may want to know whether those data are also applicable for the nanoforms. So these two guidance will be explained more in depth later on today. Also, we had some available guidance for nanomaterials already existing, but that we felt that we could improve the advice that we were giving there, mainly because of updated OECD guideline, new standards, etc. So these are the nano-specific appendix to chapters R7A, R7B, and R7C of the Guidance on Information Requirements and Chemical Safety Assessment. This guidance gives you advice on how to fulfill the information requirements for Annex 7 to 10. The appendices for nanomaterials give you nano-specific advice, and in R7A, you will have the physicochemical endpoints and the human health endpoints. In R7B, you can find the environmental endpoints, and in R7C, you have more environmental endpoints plus advice on toxicokinetics. Also, there is other rich guidance for nanomaterials that was published already a while ago in 2012 and that has not been updated, but that it is still useful if you are going to register nanomaterials. Those are also appendices to guidance on information requirements and chemical safety assessment, in this case to chapter R8, R10, and R14, and they deal with vinyl derivation, PNEC derivation, and occupational exposure estimation. As I have mentioned, all these guidance are appendices to another guidance. They are appendices to something that we call a parent guidance because they provide a specific advice for nanomaterials. So you have a guidance that gives you advice on occupational exposure estimation, and you have an appendix that gives you a specific topic for nanomaterials. So the parent guidance gives also general advice, and those principles that are in the parent guidance normally also need to be followed for nanomaterials. And also, in the nano-specific appendices, normally we only include what is different for nanomaterials, when you have to make any specific precaution or you need to use a different testing method, etc. So when no advice is given, the parent guidance should be followed. And then the only one of these documents that doesn't complement a guidance is the best practice document, because it's not a guidance, but it complements the guidance on registration, giving you best practice advice on how to distinguish between nanoforms. Also, this is not the only advice that you can find in the ECA website on nanomaterials. So on top of the guidance, we have other pages where you can find information on nanomaterials. For instance, in July this year, we launched the Nanomaterials Observatory, and this provides information on safety and market of nanomaterials. There you have a collection of information from different sources. The page will also be complemented maybe with information from other studies, and the information is presented in a user-friendly way. And there you can see some of the tabs, so you have information, user safety, etc. And the information in this nanomaterials observatory will be increasing over time. Also, we have our own website. In our own website, we also have a page dedicated to nanomaterials. There you can find general advice for nanomaterials in REACH and CLP. And also you can find links to related documents or to useful documents. So you have links to the guidance, but you also have links to Euclid manuals, to external documents, OECD, etc., to the ECA page on the nanomaterials expert group. So all that information can be found there. So this is all from my side, and now I pass the floor to my colleagues that will explain you in more detail. the guidance on nanomaterials. Thank you.
Good morning. My name is Bernadette Quinn. I work in the Directorate of Registration here in ECHA. I will give you an overview now of the recently published Best Practices Guide on how to prepare registration dossiers that cover nanoforms. So first I will outline where this Best Practices Guide fits in the registration process. The roadmap developed for the 2018 deadline is useful to illustrate the stages in the process where this guide will be useful for potential registrants. The roadmap is available on the ECHA website and addresses 7 stages for potential registrants to successfully fulfill their registration obligations. Stage 1 is Know Your Portfolio, and this is where potential registrants determine their obligations for the chemicals they manufacture or import and define their substance identity for registration. Stage 2 is Find Your Co-Registrants, and this is where potential registrants determine their joint submission and data sharing obligations according to Article 11. Stages 3 and 4 relate to CEIF formation, the collection generation of Annexes 7 to 11 information requirements to assess the hazards and risks of the substances. Stage 5 is Prepare Your Registration as a Euclid dossier. And this is where the information collected generated in the previous stages is reported in Euclid format. Stage 6 is Submit Your Registration dossier, and here the prepared Euclid dossier is submitted via ReachIT, passes business rules and technical completeness check, and the potential registrant becomes a REACH registrant once he has paid the necessary fees and reached his registration number. Stage 7 is Keep Your Registration Up to Date, and this is where registrants update the information reported as necessary, for example when they have new uses or tonnage band increases, etc. The Best Practices Guide will be useful at Stage 1, so what to consider when a substance fulfills the EU definition of a nanomaterial, and again at Stage 5, where potential registrants report substance identity information on their nanoforms in Euclid format. So the EU nanomaterial definition is given in the Commission recommendation as published on the 18th of October 2011. In the context of this guide, it is referred to as the EU definition. And this definition states, nanomaterial means a natural, incidental, or manufactured material containing particles in an unbound state or as an aggregate or as an agglomerate, and where for 50% or more of the particles in the number size distribution, one or more external dimensions is in the size range 1 nanometer to 100 nanometers. Now I will outline the context of the Best Practices Guide. It was developed to provide advice for registrations that cover nanoforms. In later slides I will outline what nanoform means in the context of this guide. It gives the recommended minimum characterization elements for substances that fulfill the EU definition, and it gives criteria to distinguish between different nanoforms, and in particular a set of elements that could be reported on the characterization of nanoforms in a Euclid dossier. Advice on fulfilling information requirements is addressed in other guidance. So these are given in the appendices for nanomaterials to chapters R6, R7A, R7B, R7C, to the guidance on information requirements and chemical safety assessment. These guidance materials are available on the ECHA website, and there are presentations in this webinar on these material. The Best Practices Guide outlines what potential registrants consider when defining their identification for substances that fulfill the EU definition, and this will be phase 1 of the registration process in the context of the registration roadmap I just showed you. The guide outlines that particle size, shape and surface chemistry are common elements for the characterization of all nanomaterials, and potential registrants would consider these on their data sharing and joint submission obligations, and by particle size in particular, whether it meets the definition of a nanomaterial, a particle's shape, and surface chemistry, which simply means the chemical nature of the surface of the particle. So what is meant by nanoform? In the context of the guide, a nanoform is a form of a substance that meets the requirements of the EU definition in terms of size and has a shape and a surface chemistry. In terms of substance identity for registration, potential registrants may decide to register their nanoforms and their non-nanoforms in one registration. The guide gives potential registrants advice on the parameters to consider when fulfilling their information requirements, so in phases 2 and 4 of this registration roadmap, and then later in technical reporting of substance identity information in particular in Euclid format. So this is phase 5 of the registration roadmap. So now we'll take you through each of the parameters given in the guide. The first one is particle size. And the first question potential registrants would consider is, Does the particle size fulfill the E definition? If yes, the substance is a nanomaterial, and they would consider shape and surface chemistry. If the answer is no, the substance is not a nanomaterial, and they will proceed as for any other substance when considering how to fulfill their information requirements. The second parameter is particle shape, and this is relevant when the substance has a particle size distribution that fulfills the E definition. Potential registrants would consider, can the shape be described as any one of the three broad shape categories that are given on the slide? These shape categories are spheroidal-like. This would be spherical particles. For example, spherical gold nanoparticles would be an example of particles that would fit into this shape category. Can they be described as having a high aspect ratio shape? For example, wires, tubes, or fibers. An example of particles that would fall into this shape category would be carbon nanotubes. Can the shape be described as being two-dimensional? So sheets, flakes, or platelets. And an example of particles that would fall into this shape category would be, for example, graphene flakes. There's a schematic representation of these shape categories given on the slide, and this is adapted from ISO terminology and has been reprinted with permission as Figure 1 in the guide. The third parameter potential registrants would consider is the particle surface chemistry. The guide outlines that due to their small particle sizes, nanomaterials have high specific surface areas, and that the chemical nature of the surface of the particle can differ from the particle interior or the core due to surface treatment. So potential registrants would consider, what is the surface chemistry? Is it the same as the particle itself, or is it different due to surface treatment? The guide outlines that surface treatment refers to the modification of the particle surface chemistry with surface treating agents. The agent can graft new functional groups to the surface. For example, alkyl groups can be grafted via silane coupling agents, or existing functional groups can be oxidized or reduced. For example, carboxyl groups on a carbon nanotube. The surface chemistry of a particle can be described via the chemistry of the agent used to modify the surface chemistry, or via the chemistry these agents impart to the particle surface. And on the right-hand side of the slide is just a very simplified, idealized schematic representation that particles with the same interior or same core chemistry can have very different surface chemistries due to surface treatment reactions. And on this slide shows a schematic of a common surface treatment reaction. So hydroxy groups on a surface react with an organosilane in solution, an organosilane surface treating agent in solution, to graft new functional groups to the surface. And this simply means the hydroxy groups are modified to alkoxysilane groups, and there are new functional groups OR-X, where OR can be an alkyl group and X can be any functional group of interest. And this is a very common surface treating reaction. And this is Figure 3 from the guide. It's given as Figure 3 in the guide. The guide outlines the minimum characterization elements potential registrants would consider once they have determined their substance fulfills the E definition. How they take nanoforms into account when fulfilling their information requirements, phases 3 and 4 in the context of the registration roadmap I showed you earlier, is addressed in other guidance material, and these will be addressed in other presentations in this webinar. The guide will be very useful at phase 5, and this refers to technical reporting in Euclid. So when you're ready to submit your registration dossier, you have to translate all of the information you have collected into Euclid format. So the guide gives technical instructions on reporting and the available fields in the substance identity section in particular of a Euclid dossier when nanoforms are within the scope of a registration. And in these slides, I will take you through screenshots of the available reporting fields in Euclid 6, where substance identity information on nanoforms can be reported. So this is a screenshot of a table of contents view of a Euclid dossier. Substance identity information is reported in Section 1. Composition records in Section 1.2 are used to report constituent identities and their concentration values. These composition records have fields to report information on the 3 characterization parameters that I mentioned: shape, size, and surface chemistry. These are called nanoform composition records in the Best Practices Guide, and the guide outlines that Euclid 6 has fields to report information on nanoform characterization parameters in the composition records, and these become editable using pick lists. So potential registrants can select solid nanomaterial from the list of options in the pick list for state or form. This will then open a subsection on characterization of nanoforms where additional information can be reported. And now I will show you some screenshots of what this looks like in practice. So this is a screenshot of the fields available in a composition record. The example is for a boundary composition of the substance record, and the state form pick list has solid nanomaterial selected. This screenshot shows the fields that become editable once solid nanomaterial is selected. There are fields to report shape and particle size range, specific surface area, and surface treatment. And now I will take you through each of the reporting fields available for each of these. The first of these is the size range reporting fields that are available. So there are fields available to report the range of particle sizes that the composition record refers to, and there are also fields available to report the percentile the values reported refer to. These will be illustrated using screenshots in the next slides. So these are the shape and particle size reporting fields, and there is a pick list for reporting the percentile, the size values reported refer to. So selecting the pick list opens a new window, and the potential registrant can select the percentile that the size values reported refer to. Size can be reported in 3 dimensions as relevant, and in Euclid terminology, they're here given as X, Y, and Z. And I will show you here. There are fields available to report the minimum and maximum value, i.e. the range, for each of these dimensions as relevant for the specific nanoform being registered. For the second parameter, there are fields for shape. Now I'll take you through the shape reporting fields. So the shape category can be reported using the pick list under shape. Selecting the pick list will open a new window where nanofiber, nanoparticle, or nanoplate can be reported. And these correspond to the shape categories given in the guide. Additional information as relevant can be reported in the remarks field. For the third parameter, surface chemistry, I will now take you to the surface chemistry reporting fields. So surface chemistry, the pick list under surface treatment, can be used to report the surface chemistry, and that's shown on this slide. Selecting none from the pick list would indicate that the particles are not surface treated. Selecting coating would indicate that the particles are surface treated. And when coating is selected, there are fields to report information on the chemistry of the agents used in the surface treating process or the chemistry they have imparted to the particle surface. So these are the fields that become editable. A screenshot of the fields that become editable once coating is selected. A name can be reported in the field, surface treatment name, and in this screenshot, the name surface treatment has been reported. Using the Add button, information on the chemistry of the surface treating agents can be reported. So clicking on Add opens a new window, and information on the layer number and the chemistry of the surface treating agent can be reported. The remarks field can be used to report any other relevant information. This is a screenshot of a hypothetical case just to simply illustrate how information in these fields can be reported. In this example, layer 1 is amorphous silica and layer 2 is polyethylene glycol, or PEG. There are also fields available to report the lipophilicity of the outermost layer. In this case, the layer 2 in the example is polyethylene glycol, and clicking on the pick list for the external layer to report the lipophilicity of the external layer will open a new window where hydrophilic, hydrophobic, or other can be reported. Polyethylene glycol is hydrophilic. It is the external layer, so hydrophilic can be reported. So in the last slides, I will show you some screenshots of how the available fields can be used to report information in composition records for a completely hypothetical case, just simply to illustrate how information can be reported. It is not a real example. So on this is a screenshot. This screenshot shows the shape and particle size range fields and the specific surface area fields. The hypothetical example refers to a fiber with 2 dimensions, in this case X and Y, under 100 nanometer. Nanofiber has been selected from the pick list for the shape, that's the shape category it falls under, and the remarks field reports hollow tube. This is a free text field. The size parameters are reported in the X, Y, and Z dimensions as relevant, and the percentile D50 has been selected to give the size ranges the percentile the size ranges reported refer to. The specific surface area on the lower part of the screen has been reported as a range, so between 1,000 and 1,300 meters squared per gram in my hypothetical example, and the remarks field was used to report additional information. In this case, it is hollow carbon fibers made by CVD, or chemical vapor deposition, and surface treated with acid to introduce carboxylate groups on the surface. This screenshot shows the surface treatment fields that are available. The coating has been selected from the pick list, and surface treatment has been reported in the surface treatment name field. The surface treatment reports sulfuric acid as the surface treating agent, and hydrophilic has been selected from the pick list for the external layer. And the remarks field reports additional information, and in this case it's the carboxylate groups on the surface enable the particle to be dispersed in water. So this concludes the presentation of the Best Practices Guide on how to prepare registration dossiers that cover nanoforms. You can find the guide in the support section of the ECHO website, and thank you for your attention.
Good morning to everyone. My name is Valeria Menta and I work in the Registration Directorate here at the European Chemical Agency. Today I will talk about the guidance on grouping read across for nanoforms. I would like to start by giving a short background on how the guidance has been developed. ECHA initiated a project in collaboration with RAVM and JRC on the usage of ecotoxicological data for bridging data gaps between nanoforms of the same substance and on grouping them. The project resulted in a scientific reference paper to which also ECHA Nanomaterial Working Group has contributed and which has been used as a starting point for the developing of the guidance. After regulatory consideration and after checking consistency with overall nanomaterial guidance, a draft guidance has been prepared internally at ECHA, which after a formal consultation procedure has led to the publication of this appendix on nanomaterials applicable to the guidance on QSAR and grouping of chemicals. So, what is the scope of the guidance? The scope of this guidance is to provide advice to registrants on how to perform grouping and read across between nano and non-nanoforms or bulk forms of the same substance. The guidance does not cover different substances directly, but the information given here may be useful when attempting read across between nanoforms of different substances. This guidance is an appendix to the guidance on QSAR and grouping of chemicals. However, not specific advice has been given here on QSAR for nanomaterials, as the state of the art at the moment does not allow to give such kind of recommendations. Now, some general issues to be highlighted. The read across terminology has been used in this guidance. However, it is acknowledged the fact that Annex 11 of the REACH regulation addresses read across between substances and not read across between forms of the same substance. However, similar principles, approach and terminology, such as the term source and target, are used for nanoforms. And the general principles in the parent guidance on QSAR and grouping of chemicals and in the read across assessment framework are also applicable here. Now, a short reminder on the terminology. Substances that have physicochemical, toxicological, and ecotoxicological properties that are likely to be similar or to follow a regular pattern may be considered as a group. And read across is a technique used to predict endpoint information for one substance by using data from a same endpoint from another substance. This guidance specifically deals with grouping a read across between nano and bulk forms of the same substance. Why guidance is needed? Nanoforms of a substance, as for all forms of substances, will need to be registered together in the same registration dossier. And the hazard posed by all possible forms of the substance that are covered by a registration must be addressed by the ecotoxicological and toxicological information presented in the registration dossier. This guidance offers a pragmatic approach on how to assess whether there are differences in the ecotoxicological properties and fate of nanoforms and bulk form. And it helps to see how to build a read-across justification and how to report it transparently and clearly in the registration dossier. Now, let's move to the core part of the guidance, where a stepwise approach for the grouping of read-across of nanoform is suggested. This is a 7-step approach, and now we will go through each of these 7 steps. And this has to be considered as a recommended approach, because also alternative approaches are possible. The steps may overlap or the order may vary, and the approach, except for step 1, is endpoint specific. And this is because grouping a read-across must be justified endpoint by endpoint. However, in practice, can happen that several endpoints can be addressed together if the hypothesis supports it, and as well as it is clearly explained that which different endpoints are covered and how and why these different endpoints are covered. The guidance follows also the principle of OECD guidance on grouping of chemicals. Now, step 1 is the identification and characterization of nanoforms. The correct characterization of the nanoforms is in fact considered fundamental for ensuring the proper hazard assessment of nanoforms. The basic information to be considered is the chemical composition of the nanoforms, including impurities and additives, as also requested by Annex 6 of the REACH regulation, but also parameters such as size and shape, and also the surface chemistry. So any surface treatment that is applied to the surface of the nanoforms will have to be considered, as you have also heard already in the auto guide on nanoforms that has been presented already. Then, after the nanoforms have been characterized, we move to step 2. In step 2, an initial grouping of the nanoform will have to be performed. So here we will have the developing of a grouping hypothesis for a certain endpoint or for certain endpoints by considering the physical-chemical parameters that I've just shown you in step 1, so chemical composition, size, shape, surface treatment. But the registrant shall at this stage also consider additional physical-chemical parameters related to the reactivity and the behavior of the nanoforms. All of these key parameters are listed and discussed in Appendix 1 of the guidance document. All the parameters need to be taken into account, but they may not be relevant for all assessment. Moreover, depending on the hypothesis, other physical-chemical parameters which are not included in Appendix 1 may be relevant, and this is the case of the rigidity parameter for fibers. Now, so this is the full list of phys-chem parameters for nanoforms. Again, you see the nanoform identification parameter, chemical composition including impurities and additives, surface chemistry, size and shape. In the identification parameter, you also see surface area, as this parameter can be used to decide if a form fulfills to the EU definition of nanomaterial. Now, it must be highlighted at this stage that difference seen in these basic identification parameters do not preclude the possibility of applying grouping and read across. So some nanoforms may have different shape, size, and surface chemistry, but still there is the possibility to apply grouping or read across. The registrant, in fact, should look at the behavior parameter, so solubility, hydrophobicity, zeta potential, dispersibility, and dustiness, and to the reactivity parameters, so biological reactivity and photoreactivity. And many times, in fact, these behavior and reactivity parameters are the ones used to substantiate the grouping or read across hypothesis for nanomaterials. It must also be highlighted that not always all these parameters have to be used for a certain grouping approach, but some of them, for example, may be used. And this will depend on the substance that we are considering, on the nanoforms, on the endpoint considered, and so on. The grouping hypothesis shall explain why similarities or differences between nanoforms in physical-chemical properties allow predicting of specific ecotoxicological and toxicological behavior. The grouping hypothesis must also include a set of inclusion and/or exclusion rules that determines the range of applicability within which reliable estimation can be made for group members for the given endpoint. For inclusion or exclusion criteria, we mean a range, for example, range of sizes, range of shapes, or range of solubility values. Physical-chemical similarity may not be enough justification for grouping approach, but it may be necessary to support the hypothesis by using toxicokinetics data, such as ADME data, screening in vitro data, and in silico models or predictions. To support the grouping hypothesis, will be also important to consider processes that influence transport behavior in different environmental compartments. And these are adsorption, desorption, heteroaggregation and heteroagglomeration, sedimentation, dispersion, and interaction with biomolecules. Now, this is a simple example of grouping approach based on solubility. So let's consider that to have some target nanoforms, where for target we mean the forms on which an endpoint is being estimated, and a source non-nanoform or bulk form, where for source we mean the form used to make the estimate. And altogether they will make the group of forms that we are considering in this approach, and all these forms are part of one substance. Now, the available information that we have on the target nanoforms is that they have an high dissolution rate, they have similar water solubility to the source, they are not surface treated, and what we know is that the systemic toxicity of the substance is driven by the release of toxic ions. Now, due to the high dissolution rate and to similar water solubility, it can be claimed that source and target have similar toxicokinetic behavior and same toxicological effect, based on the hypothesis of the ion-driven toxicity. The systemic toxicity of the target nanoforms can therefore be predicted from the available studies conducted on the source form. Further information may be needed to substantiate this hypothesis and to show similar toxicokinetic behavior, such as adsorption studies and/or dissolution rate studies in different media. Now, let's move to the next step of the approach. So after step 2, we have step 3. So all the available information on the forms that are part of the group will have to be collected. And an assessment of the adequacy and reliability of available information for each nanoform and bulk form that is part of the group will have to be done. It is important to consider here similarities and differences in behavior in the test environment, in reactivity and fate due to the variable physical-chemical properties. It is important also to check whether a reliable study is available within the group for the specific rich information requirement. If this study is not available, it will need to be generated. So, after all information has been evaluated, a data matrix will have to be prepared. The data matrix will contain endpoint considered for the grouping versus the group members. The data matrix shall indicate whether there are data available, shall indicate also which are the key study results considered, and how these key study results are used to support the grouping hypothesis. The data matrix shall also identify the data gaps. An example of such matrix is shown in Appendix 2 of the guidance document. Then we move to step 5. In step 5, a preliminary assessment of the group must be performed. So we'll need to be checked if the grouping hypothesis is supported. So if the group exhibits sufficient similarities in physical-chemical properties based on the available data in step 2. And if the group is sufficiently robust, so if it contains sufficient relevant and reliable information on the members for assessment purposes. The possible outcome of step 5 are 3. First possible outcome is that the grouping rationale is not supported. In this case, the registrant will have to go back to step 2 and will have to modify the grouping hypothesis, for example, by subdividing the group of forms. to take into consideration. The second possible outcome is that the grouping rationale is robust, but adequate data is not available. In this case, testing will have to be done on some representative nanoforms or forms part of the group. So the registrant will have to go to step 6 and generate the data. Third possible option is that the grouping rationale is robust and adequate data is available. In this case, the approach is finalized and the registrant can go to step 7 and document the approach, the justification, and the results. So, step 6. Here we are in the situation where the grouping approach is considered robust, but there is not enough data. So, the registrant will have to fill the data gap by performing tests in a conventional manner, following Annex 7 to 10 of the REACH regulation or using adaptation as foreseen in Annex 11 of the REACH regulation. If normal tests are performed, it is extremely important to check the adequacy of the test method for the specific information requirement and the adequacy of the testing material, which must be representative of the nanoforms or of the forms that are considered within the group. And the testing proposal may be required if the tests are one of the one listed in Annex 9 or 10 of the REACH regulation. Once the data have been generated, they will have to be checked again for adequacy. After the assessment has been finalized, it is extremely important that the assessment is clearly and transparently documented in the registration dossier. The registrant can do this by using the Euclid Assessment Entity functionality, which is a tool available in Euclid 6. The assessment must be reported transparently in a way that the assessor can well follow the logic of the assessment and shall explain how the uncertainty has been addressed in the assessment. This is all from my side, and thank you very much for your attention.
Hello, I'm Camelia Constantin from Directorate of Evaluation, and I'm going to present you the main changes that were made in the updated guidance for nanomaterials with regard to the human health endpoints. I have to say that the advice does not exclude the parent guidance advice, and if there is no advice on a specific endpoint, then the parent guidance advice would apply. The update prepared in this guidance covered the sections of appendices to chapters R7A for the human health endpoints and R7C for toxicokinetics, and also includes new sections. A new addition in this current version of the guidance is the decision tree for the testing for human health endpoints. This testing strategy is dependent on the dissolution potential in relevant biological fluids and testing media. It does not propose cutoff values. However, dissolution rate needs to be close to instantly dissolved. The determination of dissolution rate is not important only in the context of this decision tree, but it also gives useful insight on how a certain particle may interact with its biological environment. How the decision tree works. If you have a substance which by physicochemical characterization seems to be a nanomaterial, and if it has a fast dissolution rate in the biological fluid that is close to instantly dissolved, then the advice in this document, in the appendix to the chapter R7A, applies. If the substance is not fulfilling the criteria for a nanomaterial by physicochemical characterization, then the advice in the parent guidance apply. Also, if there is a fast dissolution rate in the biological fluids, then the advice in the parent guidance apply. I apologize, I guess that I said before that if it's a fast dissolution rate, then the advice in this document applies. It's the other way around. So fast dissolution rate, then the advice from the parent guidance applies. And if there is no fast dissolution rate, then the advice included in this updated guidance apply. The introductory section on advisory note has been updated and expanded. And a new addition is related to the reporting of the parameters needed in the endpoint study record. And they refer to the chemical composition as it is described in the guidance for identification and naming of substances under REACH and classification, labeling and packaging regulation. The size, as a minimum, the D50 needs to be reported. However, a particle size distribution is recommended to be included. Shape and aspect ratio, surface chemistry, all these are important information to be present in the endpoint study record because they allow to understand the outcome of the study and also allows to compare and to link the results obtained in this study with the results obtained in other studies performed with similar forms. Also, advice is given on the biological sampling. The samples generated in vivo toxicological studies should be collected according to the OECD testing guidelines. However, if there is an indication that the nanomaterials would distribute in other tissues which are not listed in the testing guidelines, then the collection of additional tissues is recommended. Also, it is recommended to keep samples to allow for later analysis. For example, storage by chemical or physical tissue fixation for microscopy or freezing for burden analysis at a later stage. The advisory note includes now also a section on the use of non-animal testing approaches. And this is in fact an updated and expanded section which used to be present in the end of the individual endpoints in the previous version. So this is now included in the advisory note. And it recommends to follow the ongoing developments and validation efforts made by OECD and the European Union Reference Laboratory for Alternatives to Animal Testing, and also to monitor the regulatory acceptance of these new methods that are generated. It is important to acknowledge that the implementation of the non-animal approaches require prior consideration of all available information, including context-specific characterization, and this is a critical factor for the grouping, read-across, and QSARs. Also, the results generating from non-testing and in vitro methods are useful in the context of weight of evidence approach and also give key information when planning a new animal test. So far, these are the changes that are made for the general section of the guidance. For the individual endpoints, I will present you in the next slides, and I will start with the section of repeated dose toxicity. This section recommends that the testing should be performed via inhalation unless there is convincing information, for example, on the basis of the uses or dissolution rate, which would justify the use of another route. Any modification that is made to the protocols that are described in the OECD inhalation testing guidelines 412 and 413 should be justified and appear clearly reported. Regarding the dose range finding studies or repeated dose studies performed with the poorly soluble particles, it is recommended to collect additional toxicokinetic data. These recommendations are also in line with the current specifications from the updated testing guidelines for inhalation toxicity, which were recently adapted for the nanomaterial testing. And also it is recommended to consult the recommendations for nanomaterials which are applicable to chapter R7C, which treats the toxicokinetics. Data on lung burden and clearance may be also useful arguments in the context of read-across argumentation. For the poorly soluble particles, it is recommended to collect samples at several time points. This is again in line with the current specifications of the updated OECD testing guidelines for inhalation, or to collect samples from different organs than the others specified in the testing guideline, if needed. While the use of extra animals for additional analysis is generally not recommended, it is important to balance between performing additional analysis and following an indication of toxicity. The bronchoalveolar lavage analysis is recommended, and this again is in line with the current specifications of the updated testing guidelines, OECD testing guidelines, where this analysis became mandatory for nanomaterials testing. Also, it is recommended to use more than one different dose describing metric. However, you should always include the mass metric. The advisory note with consideration on the lung burden within inhalation toxicity assessment used to be a standalone chapter. Now it has been moved under the section of repeated dose toxicity. And the scientific background has been redrafted to include the up-to-date knowledge and has been shortened for more clarity. It includes reference to the maximum tolerated dose, which is very important for the new studies, as well as dosimetry considerations. It also clarifies when advice is relevant for the interpretation of already available information. As I said, while mass is always required, it advises to use more than one different dose describing metrics. This is very important to be able to appropriately interpret the outcome of the toxicological results. The choice for the selected method and metric should be justified. This section also includes an overview of recommendations for the lung burden. Another endpoint that has been updated in the current version of the guidance is the mutagenicity, and this section now includes the note which was previously separated with regard to the interference for the bacterial assay, and also the recommendations that were done for genetic toxicity testing in a workshop organized by OECD and the Working Party of Manufactured Nanomaterials from 2013. And these recommendations, I'm going to present them to you in a couple of slides. AIMS test, the testing guideline 471, is not to be recommended for nanomaterials. The measures of cytotoxicity based on cell proliferation as described in the testing guidelines are found appropriate for determining top concentration for in vitro testing of nanomaterial. Also, it is concluded that the extent of cellular uptake is critical to interpret the results. With regard to in vitro micronucleus test, if cytocalasine B is used, it should be added post-treatment or delayed co-treatment. This is to ensure a period of exposure of the cell culture system to the nanomaterials in the absence of cytokalasin B. So this is an important recommended modification for this test. Before starting any in vivo genotoxicity study, toxicokinetic investigations are needed to determine if nanomaterial reaches the target tissue, if the target tissue is not the site of contact. Without any toxicokinetic information, the genotoxic effects should be investigated in the site of contact tissue. The selected route of administration must be justified, and the exposure of target tissues need to be addressed. As I mentioned earlier, also the appendix R7C on toxicokinetic has been updated, and in this section it is acknowledged that detecting and quantifying nanomaterials in biological tissues is analytically and technically challenging. Therefore, the method used and their limitation needs to be adequately documented, so they are well understood for relevance. Solubility and dissolution rate in relevant biological fluids and testing media is essential in order to understand a particle's kinetic. For poorly soluble particles, the information on translocation across biological barrier is essential. Toxicokinetics data are not an intrinsic information which is valuable to understand the toxicological data, but it's also very valuable to justify the use of these data between different forms of a substance. It is recommended to collect as much toxicokinetic data as possible from the experiments already required under REACH. And again, it is important to balance between performing additional analysis and following an indication of toxicity. To summarize, the main changes that were done in the general advisory note refers to introduction of a decision tree based on solubility and dissolution, which is a starting point for nanomaterial testing. Then the advisory note on testing and sampling strategy and sample preparation has been updated, expanded, and includes new recommendations. And also the general advice for non-testing methods has been reorganized and included under section 311 instead of being repeated in the at a separate endpoint. For the individual endpoints, there was an update on the consideration on the advisory note on consideration of lung overload, on the repeated dose toxicity section, and on mutagenicity section, where the information on bacterial assay interference was relocated, and which includes now the general recommendations for mutagenicity testing agreed at the workshop organized by OECD and the Working Party on Manufactured Nanomaterials in November 2013. And also the appendix R7C on toxicokinetics has been expanded and updated with up-to-date information. Thank you.
Good morning or good day. So I will finish this serial of presentations with the environmental endpoints update. With regard to the three chapters that you can see in this slide, the chapter R7A, or the sections that were updated, were mainly physicochemical endpoints covering these, but they have been updated with regard to their environmental relevance. R7B and R7C, as mentioned by Celia, are covering ecotoxicological and fate endpoints for every environmental compartment. Moving to the appendix of chapter R7A. Please note that all these endpoints, the ones you can see on the slides, were updated, except the granulometry, which is still at the version 1, so the one of 2012. So we have updated the sample preparation, adding some nanospecific considerations, and in particular on the choice of the testing material, so that whenever you want to choose some testing material, it has to be representative of the registered substance, and or it has to be also relevant for the nanoform you want to test. Where you also need to take into account and provide the chemical composition and the characterization, as already explained by my colleagues, on the particle size, the shape, the aspect ratio, and the surface chemistry. You need also to provide and take into account the characterization of the physico-chemical properties and their state when present in test medium. And in this case, for the environment, of particular relevance are the degree of agglomeration and potential sedimentation. Now some aparté about this sample preparation. Here you can find this slide and the next one, where I will explain all the different OECD guidance or test guidelines documents that are referred here in this chapter R7A, but also all along the 3 environmental appendices. Starting by the OECD guidance 23, which is the one for the aquatic difficult to test substances. And by this by this assumption that the applicability of this guidance for the polysoluble substances is very limited. So it's very limited for nanomaterials. Therefore, we provided the advice to follow the guidance on the sample preparation and dosimetry, the so-called OECD 36, but also the report on the ecotoxicology and environmental fate of the nanomaterials. So the report and its addendum. Further on, in this chapter and in the others, there are references on guidance documents and test guidelines that are for the moment either under development or finalization. And since the publication of this guidance update, one test guideline was adopted. It's the first one you see on the slide, the OECD test guideline 318, which is on the dispersion stability of nanomaterials. So you can apply it if you want. Now moving to the subsection that was added under the sample preparation, and which is called the general considerations for ecotoxicological testing. We provided the advice on what to do when you want to perform some test for eco or toxicological testing purposes. So you need to define the physico-chemical properties and the potential eco or toxicological effects that they would have or could have when they interact with the test media. You also need to take into account when preparing your test item the dispersion and its stability. And in particular, depending one more time on the type of test media you want to put this test sample in. And then the testing has to be carried out with different analytic methods in order to monitor the exposure concentration. In this sense, the use of only the chemical analysis is not sufficient, which in practice means that when using dose metrics, the most appropriate ones may not be known, and in particular the dose matrix, which is usually the mass-based, is not sufficient for nanomaterials. So we advise to take into account or consider in parallel the surface area and the particle counts. And last but not least, for the considerations before testing, you need to also select a sample preparation procedure and the controls you want to apply, and provide a thoroughly justified justification and also a good reporting in the robust study summary of your Euclid dossier. Now moving to the physico-chemical endpoints, and starting by the water solubility. So this endpoint is defined in the parent guidance in this section R717. And the main test guideline that is advised for assessing the water solubility is the test guideline 105, which is in most cases not appropriate for the testing of nanomaterials. Therefore, the dissolution rate and the degree of dispersion are very important information to be known on the substance. Nevertheless, there are exceptions, so moments where the measurement of the water solubility as per OECD test guideline 105 may be of value for nanomaterials. And this is in the case where these nanomaterials have a high and fast dissolution rate. In these cases, then the water solubility could be used as the endpoint and the entry for this information. Nevertheless, you need also to take into account the solubility and the dispersibility, and in particular that there are different and distinct phenomena, as explained by my colleague, especially for the read-across, and they have different implications in the testing and the characterization of your nanomaterials. For the water solubility, we also added some information on other guidelines and protocols that could be used once they will be available. These guidelines and protocols are also, or these alternative parameters are also indicated for the next endpoints for the partition coefficients. So these are the test guideline on the dissolution rate of nanomaterials and the OECD guidance overarching between the agglomeration or the dispersion and dissolution behavior. We strongly advise to follow them once they will be released. Then the last part is about alternative or adaptation, and it's this waiver, which is the insolubility, which cannot be used on its own. And whenever you want to apply some waiver, you need, besides this insolubility, to provide a robust technical and scientific justification, including different considerations. For instance, what is the agglomeration behavior and the dissolution of your nanomaterials. For the last two endpoints of the chapter R7A, the partition coefficients, we have two partition coefficients. One is called N-octanol water, but it's also called KOW, and the adsorption-desorption between soil and water, which is also named KOC. For both of them, they are not applicable to nanomaterials in most of the cases. The conditions when these would be applicable are similar to the one for the water solubility. In other words, your substance needs to have a high and fast dissolution rate. So it needs to be very water soluble. And there are alternative parameters under development that can be used as weight of evidence. And these are, as I mentioned them, the agglomeration behavior, the dissolution rate, the attachment efficiency, and the sedimentation. You're not obliged to provide them all, but this is a list. There are also models that are under development, but they start to be calibrated, and we provided them as an appendix. You can see the names here, simple box for nano, or steady state distribution model. You can also use them as part of the weight of evidence approach. And in order to decide if you want to perform an alternative testing strategy in the environmental compartment. Now moving to the chapter R7B, we have in this chapter a few updates specific to the endpoints, so the aquatic and the sediment endpoints, but also to the fate ones, so covering all the degradation steps. But as a beginning, we added a general advice on how to perform ecotoxicity and fate testing, which is of course cross-linked to the R7A, with references to the sample preparation and the conditions for monitoring or the use of metrics. Basically, what you need to do before considering ecotoxicity and fate testing is to define representative controls, consider the dissolution rate and the potential ion release in case of inorganics or organometallics nanomaterials, consider the agglomeration behavior, what would be potentially the degradation and transformation of your nanomaterials. Also, to provide a justification for the selected exposure regimes. Here, the regimes means, do you want to do a static, semi-static, or flow-through test when you want to test in the water or the sediment? And of course, confirm what is the level of exposure during the study. So, do a good monitoring. When moving to the aquatic compartment and aquatic toxicity tests, there are a few waivers that can be used. The first one is the high insolubility. But unlike the one for the water solubility in R7A, it cannot be used on its own. You need to provide additional justification. So, to consider what would be the dispersion, the dissolution, and the agglomeration behavior of the nanomaterials. You also need to confirm or to check that the test guideline chosen is applicable for nanomaterial testing. For aquatic toxicity, we have a preference of long-term testing versus the acute or short-term testing due to longer exposure, so more certainty that the organism will be exposed long enough to the nanomaterial. I also put there some recommendations of additional endpoints that are specific to the different test organisms. So this is a list, and it is not exhaustive, and it is just a list of recommendations. So for the fish, besides the usual apical parameters, the mechanical effects could be considered. The histopathology also of the fish could be also added in the testing. For the algae, the shading effects is very important and need to be accounted for. There is also the possibility to consider other measurements than the chlorophyll A, such as the fluorescence measurements. And the oxidative stress and membrane damage could be also considered besides the normal testing. For Daphnia or aquatic invertebrates, the nutrient depletion has to be accounted for, and the sex ratio parameter could be also sampled and followed. There is also the possibility to check if there is any adherence of your nanomaterials to the organism. And for all these organisms, there is also this effect that needs to be accounted prior to the testing, which is the potential toxicity of the nanomaterials due to their photocatalytic effects. Now moving to the sediment compartments and the testing. When talking about the sediment compartments, there is this approach which is called the equilibrium partitioning method. This one is relying on equilibrium, thermodynamic first of all, and second of all on the use of log KOW. So it has a very limited applicability when talking about nanomaterials. And here there is an extra complication, which is to consider the potential interactions of the nanomaterials with the sediment, and also what would be their related transformation products. We provided also advice on how to select appropriate spiking method, which can be summarized as direct or indirect, but I will give later on some examples. And for these OECD test guidelines on the sediment organism, all the guidelines mentioned underneath, so the 225, 218, and 233, are the ones that were found to be generally applicable for nanomaterials. So you can choose them depending on what you want to test, whatever your type of nanomaterial is. Moving to the fate parameters, the main one or the main processes are covered by the degradation. Degradation can be abiotic or biotic. And starting by the biotic part, the biodegradability is usually applied to organic substances. But of course, it's of limited or no meaning when you talk about inorganic substances, and here we include inorganic nanomaterials. Nevertheless, there is always the possibility for the carbon-based nanomaterials to apply some biodegradation study, or at least provide justification why you did not consider them adequate for degradation. So as I was saying, degradation is covering biotic and abiotic degradation. And there are in some cases, relevant processes for nanomaterials and coatings abiotic degradation. And these are the hydrolysis, the oxidation, and the photocatalytic degradation. But you also need to consider, besides this, the degradation and potentially transformation assessment of the organic nanomaterials, but also the coating agent or functionalization agent of your nanomaterial. Then we also added some subsection about the transformation parameters. At the time being, the quantitative methods available for transformation are still scarce, but you can always apply qualitative assessment as it is useful. And when talking about transformation, you need to it is considered relevant, especially for the surface chemistry of the nanomaterials or the coating agent. And here you can see some relevant transformation processes that are influenced by the fate and they are influencing the fate and the behavior of the nanomaterials. It's quite lengthy, so I won't name them all, but some of them are quite known or basic, such as the adsorption and desorption to other substances, and others are also under scrutiny, such as the corona formation. So this is the list. And now moving to the last chapter, the chapter R7C, where we have updated the non-testing and testing of the bioaccumulation. So it's a fate endpoint, another one. And the last environmental compartment, the terrestrial one. So for the non-testing data of bioaccumulation, another statement that might sound a bit repetitive is that it is not possible to make bioaccumulation estimations based on the log KW or the solubility of nanomaterials, since most of the time they are dispersed and not in solution, as I mentioned briefly about in R7A. It's also not possible to make bioaccumulation estimations based on log KW, because log KW is, in most of the cases, not adequate for nanomaterials. So if you want to waive the bioaccumulation test in fish based on the log KW, log KOC, or another screening methods, it's in most cases inappropriate. But there are alternative approaches and the models that are under development and can be used as weight of evidence. And here you can see I mentioned the appendix 1 of R7A, which is this list of models. When moving to the testing, so in this case testing in fish, the BCF or bioconcentration factor cannot be calculated, as there is no thermodynamic equilibrium reached between the organism and the water phase, and a stable concentration of the nanomaterials cannot be maintained. So you cannot really go for thermodynamic equilibrium when you have nanomaterials in water phase. So the OECD test guideline 305, which is the fish bioconcentration test, is not applicable for the nanomaterials if you use the aquatic exposure route, because most of the time they remain as particles. You always have the exception in case you have a nanomaterial that would have a high and fast dissolution rate, and in this case the parent guidance would apply. Then moving to the other type of exposure route, this OECD test guideline 305 via the dietary route is partially applicable. In the meantime, there is a guidance on the assessment of apparent accumulation potential of nanomaterials that is under development and soon to be finalized. That should help to decide which one is the best one. But you also have the possibility to use alternative methods. And these are the OECD test guideline 315 and the 317, which respectively are the bioaccumulation on sediment oligochaetes or terrestrial oligochaetes. Whatever your choice is, 305, 315, 317, you have to bear in mind that you really need to perform a proper monitoring of the exposure during the test. And now the last compartment, the terrestrial toxicity. So for the non-testing data, as I said for the sediment, there is a very limited applicability of the equilibrium partitioning method. In the meantime, we don't have, for the moment, established other estimation methods available, and this includes the QSARs that are not validated or not available at that moment. But you can always choose to apply the guidance for grouping, as was explained by my colleague Valeria. And you can try to apply weight of evidence using different approaches. So this is a case-by-case assessment. When moving to the testing data, all the methods described in the parent guidance R711 for this terrestrial toxicity are in principle applicable for testing nanomaterials. Whenever you want to do some terrestrial toxicity testing, you need to follow the R7A or R7B in the sense that you need to decide and report in detail what is the sample preparation you have chosen and which spiking method you did choose. For the spiking methods, there are different types. It can be direct or indirect. But to spice it up, we provided some extra information, for instance, that you can choose the aquatic dispersion into soil, which is called the wet spiking, or you can disperse it directly in the test media, so it's called dry spiking. So this will be a dry and direct. But there is also another way, which is to put this on a carrier, which can be the sand or spiked food. And one more time, this is high indirect. You can look at the appendix for this. And as I said, because you need to follow you need to report and justify which type of sample preparation you did, it's quite obvious that you would need to follow the recommendations set out in the OECD 36 and the OECD 40. And sorry for repeating, but this is a kind of take-home message. Whenever you do any kind of testing in the environment, you need also to perform proper monitoring and ensure that you have a proper exposure of the organism during the tests. Thank you.